Everyone, welcome to the Chemistry channel. So today we're going to be starting our series of lectures on atomic structure. So this lecture is going to primarily focus on wave properties in light. Now, light is a very important concept to understand in order to have an understanding of atomic structure, because with our understanding of light, we have been able to deduce many of the concepts of atomic structure. So an understanding of light is very key in order to understand atomic structure. So with that, let us begin. So what is light? Well, light is a transverse electromagnetic wave. So there's a couple of big words in here: transverse and electromagnetic. So let's look into what these words actually mean. So what is an electromagnetic wave? An electromagnetic wave is a wave in which the electric field vectors and the magnetic field vectors oscillate perpendicularly to the direction of propagation. So there's also a lot of big words in here as well. So let's sort of give you a rudimentary understanding of an electromagnetic wave. So here we have a little diagram showing you what an electromagnetic wave looks like. So in here you'll see two waves: this blue wave, which is oscillating in the y direction, and this red wave, which is oscillating in the z direction. Now let's take a look at this blue wave here. This blue wave symbolizes the electric field vectors oscillating. So what's an electric field? Well, if you think about it, we have positive charges and negative charges. Now, positive charges are defined to have an electric field that points outward. So what does this mean? Well, classically, current was actually used to be thought of as moving positive charges. So believe it or not, a long time ago, people used to think that current was the movement of positive charges. Now, with our greater understanding, we now know that it's electrons that move, but however, back then, they actually thought that the positively charged species are what provided current. So, in order to define electric field, they showed that electric field vectors point out of positively charged species. So what does this actually mean? This means that if a positive charge approached this positive charge here, the field vectors, or the force, would cause the positive charge to be pushed and repelled away from the source charge. So these lines radiating outward from the positive charge represent the electric field vectors. Now, electrons have the opposite electric field. The electric field lines point inward for electrons, and that's because if you have a positive charge near the negative charge, the positive charge is drawn towards that negative charge. So that's sort of the basic idea of electric field. So once again, electric field vectors are these vectors which basically show where a positive charge would move in relation to a source charge. So you don't really have to have an understanding of what these waves are for chemistry. It's just interesting to have a basic idea of. You're going to get more into that once you go into physics, or if you are in physics already, you'll probably discuss electric field vectors. So this red line represents the magnetic field vectors. Now, magnetic field vectors are very similar to that of electric field. You're probably familiar with magnetic fields whenever you play with magnets. So it's important to note that whenever a charge moves, it can create a magnetic field. So therefore, in an electromagnetic wave, you have both of these electric field vectors and magnetic field vectors oscillating. So that's sort of what those two things mean. Now, what is this direction of propagation? Well, the direction of propagation basically means which way the wave is traveling. Now, we can see from this figure that I have here that the wave is traveling in this direction, so I'll outline it in pink. So the wave is traveling in this direction. So this is the wave propagation direction. And if you look at the magnetic field vectors and the electric field vectors, you'll see, so I'll sort of extend this all the way here, that they both form 90-degree angles with the wave propagation direction. So that's why we say they oscillate perpendicularly to the direction of propagation. So that is sort of what those terms mean. As a general chemistry student, you won't have to know what an electric field or a magnetic field is, most likely. That's more towards physics classes. However, though, it helps you to understand light a little bit better. So I talked about a transverse wave. So what is a transverse wave? A transverse wave is a wave in which the species oscillates perpendicular, so this means perpendicular, to the direction of propagation. So we already sort of described this in our figure here. So we see here that both the electric field vectors and the magnetic field vectors are perpendicular to the wave propagation direction. So that's why electromagnetic waves are called transverse waves. So we're talking a lot about waves, right? Well, let's go into the properties of waves. So this is something that you will need to know for general chemistry. So the first thing that we should define is something called the wavelength. So the wavelength is the distance between two adjacent peaks or two adjacent troughs. So what do I mean by peaks and troughs? Well, on this diagram here, this is a peak. So this is a peak, and this is a trough. And troughs are sometimes called valleys as well. So this is sometimes called a valley. So these are the troughs and these are the peaks. Therefore, the wavelength can be measured from peak to peak or from trough to the next trough. So this distance here between this peak and this peak is the wavelength. And this symbol right here, lambda, is the symbol for wavelength. So you'll often see lambda in equations. So lambda is the wavelength. So I can put that here. So wavelength is symbolized by lambda. So this is the wavelength because this is the distance between two adjacent peaks. So the next important thing to note is amplitude. Amplitude is the maximum displacement of the wave from the equilibrium, so this means equilibrium position. So let's talk about that. So this right here, this line, so I'll actually highlight it in pink. So this line that I'm highlighting is called the equilibrium position. So the equilibrium position, actually I want the pen, so let's get the pen. So this pink line is the equilibrium position. So what is the equilibrium position? The equilibrium position is the position where the wave oscillates around. So you can see that this is the equilibrium position on this figure here, because the wave is oscillating around this black line here. So we were talking about amplitude, right? Well, the amplitude, we said, is the maximum displacement from the equilibrium position. So there's actually two forms of amplitude. So this right here is the minimum amplitude. So this whole line measures the minimum amplitude, and it's the minimum because it's on the negative side of the graph. So it's below 0, so that's why it's called minimum. And there's also the maximum. I'll just put max amplitude, and that symbolizes amplitude. And this is the max amplitude because it is on the positive side. So this whole distance here represents the amplitudes. Okay, and you can see here that they are oscillating around this equilibrium position. So the last thing that I want to define are nodes. So nodes are points in which no displacement, so sorry about that, in which no displacement takes place. So these nodes can often be found where the wave intersects with the equilibrium position. So all these orange dots here, as you can see right here, here, and here, and here are nodes. So that's a node. And anywhere where the wave intersects with the equilibrium position is a node. And those are areas where no displacement takes place. So, now that we know the properties of a wave, we can actually start talking about its applications. So the first thing that you have to know is the frequency of something. So what is the frequency of something? The frequency of something is the number of wavelengths. Now they have to be complete wavelengths, so I'll put a little parentheses. Complete. The number of complete wavelengths that pass through a point in a certain amount of time. And the SI unit for the unit for frequency is often called Hertz, which equals 1/seconds. So that is the unit for frequency, Hertz. You'll often see it in Hertz. So frequency is therefore equal to the number of wavelengths that pass through a point per second. Now it's important to note that the top number, since it's only a number, is unitless. The only part of the equation that has a unit associated with it is the denominator. So that's why frequency has 1 over seconds, or seconds to the -1 as its unit, okay? So the other thing that you should know is period. And period is actually equal to 1 over the frequency. So it's equal to the amount of seconds per number of wavelengths that pass through a point. So period can be defined as the amount of time it takes for one cycle to take place. So one cycle means one wavelength. So it basically tells you the amount of time per wavelength to pass. So that's what a cycle is, the amount of time for one wavelength to pass. So it's the amount of time it takes for one cycle or one wavelength to pass or to take place. So it's just the inverse of frequency. Okay? So, use the frequency to measure the speed of a wave. And this speed is called the propagation speed, or the speed at which a wave travels. So that is the propagation speed. Now the formula for propagation speed is lambda times the frequency, where this little mu type symbol here represents the propagation speed. Lambda is equal to the wavelength, and f, of course, is equal to the frequency. So why does this equation work? So instead of having you memorize it, let's understand why this equation is written in such a way. So you may know that speed is equal to the distance over time, right? So speed is distance over time. Well, we know that lambda, which is equal to wavelength, is a distance. So wavelength is a distance, right? And we know that frequency is equal to the number of wavelengths that pass through a certain point per second. Now this numerator, as we said, is unitless. The only unit in frequency is the seconds. So let's multiply these two things together and see if we get speed, the units of speed. So let's do this together. So when we multiply lambda times f, what you're doing is lambda times the number of wavelengths per second. Now remember, this numerator is unitless. So therefore, you can just look at this numerator as a unitless factor. So it could be like 1, 2, 3, 4, etc. So since lambda is equal to x, we can substitute in x times number of wavelengths per second. And now when we put this together, we get x over s times that unitless factor that we were talking about. So therefore, you see that when we multiply these two things together, you get speed, right? So that's why this equation works, okay? So now let's take what we learned and apply it to light itself. So let's change my color here. So in a vacuum, the speed of light is a constant. And the speed of light has actually been found to equal 2.998 times 10 to the 8th meters per second. So that's really, really, really fast. And the symbol for light is C. So the speed of light is always constant in a vacuum. And the speed of light is given the symbol C, and it's equal to 2.998 times 10 to the 8th meters per second. You'll often see it rounded to 3.0 times 10 to the 8th meters per second. Okay, so now we know that the speed of light is a constant in a vacuum. So what does this mean for our equation that we have up here? Well, this means that the propagation speed, so remember that this is the propagation speed, this means propagation speed. Since the speed of light is constant, its propagation speed is constant. Therefore, for light we can set this mu equal to c. Therefore, c is equal to lambda times f. And we can do this, we can set this equal to c because c is a constant in a vacuum. Now, because light is constant in a vacuum, we can come up with some certain relationships based upon this equation. So c is equal to lambda times f. This allows us to predict how frequency and wavelength affect each other. And this is going to be very important later on. So from this equation, since the speed of light or c is a constant, we can make these predictions. So since the speed of light c is a constant, as the frequency increases, in order to keep the speed of light constant, the wavelength must decrease. So as the frequency increases, the wavelength must decrease. And this relationship occurs in order to keep the speed of light constant, because as frequency increases, the wavelength must decrease in order to keep the speed of light constant. Now the reverse is true as well. As frequency decreases, the wavelength must increase. And now that is because as the wavelength increases, in order to keep the speed of light constant, the frequency must decrease. Therefore, we can come up with this general idea. The shorter the wavelength, the larger the frequency. And this idea is going to be very important later on. Okay, so the last topic for today is wavelengths of light. Now, light, as you know it, has many different wavelengths. I mean, if you've ever taken a prism and you've seen the light diffract from that prism, you'll see all the different colors of light. These wavelengths of light have different properties. So the different wavelengths have different properties. However, it is important to note that every single wavelength of light moves at the same speed in a vacuum. So all wavelengths of light move at the same speed in a vacuum. And this speed in a vacuum is c, which is 3.00 times 10 to the 8th meters per second, around there. So all wavelengths of light in a vacuum, no matter what the wavelength is, move at this speed. Okay? So what physicists and chemists have done is basically organize these different wavelengths into a chart. And this chart is called the electromagnetic spectrum. And it is shown right here. So I don't think many professors will have you memorize the wavelengths of things or the frequencies. I think it's just important to have a general idea of where things lie on the spectrum. So in here, I have it organized in a particular way. So let's draw an arrow this way. So the electromagnetic, all of these different groups here represent different electromagnetic waves or different wavelengths of light. So radio waves actually have the lowest frequency and the highest wavelength. And at the other end of the spectrum are gamma rays, which have the highest frequency and lowest wavelength. And remember, this is so that we can keep the speed of light constant. So as we move from left to right on this particular spectrum, the frequency increases and the wavelength decreases. So as we move from left to right here, okay, on this spectrum. And now this also applies to the visible region of light. Now, believe it or not, us as humans cannot see a lot of the light that is present in our universe. We can only see this small portion of light, which extends from around the mid 400 nanometer region to around the 750 nanometer region. So hence violet to red. Violet is the highest frequency and lowest wavelength, while red has the lowest frequency and highest wavelength. And this is also moving in the same direction as the spectrum above. So as we move from red to violet, you have increasing frequency and decreasing wavelength. So once again, I don't think it's that important to have to memorize all of the different wavelengths and frequencies. I think it's just important to have a general idea of where things lie. And of course, if your professor wants you to memorize them, please do. So that concludes our concepts for today. In the next video, we're going to be talking about the quantization of energy and the photoelectric effect and all that fun stuff, and then we'll move on into the atom eventually. So all of this will prove to be very important when we actually talk about atomic structure. Now, atomic structure is very important. It allows us to understand how atoms behave. Therefore, these are a series of very exciting lectures. This is some of my favorite topics personally. So thank you guys for watching. I hope to see you next time. Good luck in your studies, and see you in the next video, guys.